Hello, and welcome to this Introduction to Functional Neuroanatomy video. Today we're talking about orientation and planes of section. So using anatomical language to describe where we are in the nervous system, and planes of section, how we slice the nervous system up in sections to study internal structure. Since I often teach this at the beginning of September when people are coming back to class, this is my awkward Yeti cartoon for the day, heart and brain in opposition to one another. Awkward Yeti is smack full of very nerdy anatomical humor I highly recommend. So anatomical terms of direction we use to describe the nervous system are pretty simple in most animals other than us humans. So in animals without a pronounced cephalic flexure, that big bend at the front that humans develop embryonically to fit our big forebrain in, the same terms apply no matter where you are in the animal. We can see this lizard, here's his or its nervous system stretched out linearly, relatively along the long axis of the body, and we can describe that nervous system, or indeed any part of the lizard's body, using four paired sets of terms. So superior and inferior are above and below, anterior and posterior, front and back. Dorsal and ventral mean the back of the animal, not necessarily behind, but the back of the animal, and the belly of the animal is those translations. And rostral and caudal mean toward the beak or the nose, most of us don't have a beak, and the tail. And so rostrum is Latin for beak, right? So toward the nose or toward the tail. And so with these definitions, then we can see how the synonyms work, right? So because it's toward the back of the animal, dorsal is synonymous with superior. So dorsal and superior are synonymous. Because it's toward the beak of the animal, anterior and rostral are synonymous in most animals throughout the nervous system. In humans, the meanings of dorsal-ventral and rostral-caudal change at the midbrain diencephalic junction. So this is the crucial point where those terms of direction change. Just these two pairs. So we call these the variable axes. And these terms over here that never change are the fixed axes. So those mean the same no matter where you are. The variable axes change at this junction. Above the midbrain diencephalic junction, these are the terms of direction you use. So everything shown in red is above the junction. Everything shown in yellow is below that junction. So let's see what that looks like. So the fixed axes, again, they are the same. Superior and inferior, anterior and posterior, and one more, medial and lateral. Medial toward the midline, and we're talking about this midline, the mid-sagittal plane, and lateral away from the midline. Those are fixed. You use those terms the same way no matter where you are in the nervous system. The variable axes are the ones that change at this midbrain diencephalic junction. And so for variable axes, that's the landmark, right? And you can see the example is shown here. So below that junction, rostral and caudal are here, and they're synonymous with superior and inferior. Above that junction, here's rostral, here's caudal, and it's synonymous with anterior and posterior. So you can see how those terms change. There's one additional term that proximal distal, it's an anatomical term. It is used in neuroanatomy, albeit less commonly in the central nervous system. So think about examples of where you could use proximal distal to describe neuroanatomy. And if you're in my course, we'll talk about the answers in tutorial. And so here's some more questions for you. Here we've got a fresh brain. You don't often see brains like this. It's still full of blood. And we're looking down on it. So I challenge you to use two terms to describe this view of the brain. What is the view of the brain? which is the anterior side of this image, and how can you tell? And at this level of the CNS, what is the synonym for anterior? So 3 questions. It's so cool to see the brain like this because you can see the vasculature that's full of blood overlying the brain. And you can actually see, which you don't get to see in a fixed brain so beautifully, the delineation between the gray matter overlying the cerebrum and the white matter deep to the gray matter. So here's some examples of how we use these relative terms of direction in the human nervous system. Right? Again, these are the fixed axes over here in black, and these are the variable axes over here. And you can see how you use them changes slightly above and below this junction. And so we could use 2 terms to fill in this blank. So I'll start the first one. The diencephalon is blank to the primary visual cortex. How would you do that? Well, the diencephalon is here. There's the thalamus, so I can see that I'm looking at diencephalon. And I see that the diencephalon is above that crucial junction. So here are the axes that I'm going to use. Of course, I know the primary visual cortex is sort of, I'm squinting because I'm old, somewhere back here, right at the back of the brain in the occipital lobe. And so I could use 2 terms to describe this relative position. I could say the diencephalon is rostral to the primary visual cortex, or I could say it's anterior to the primary visual cortex. And so those are the sets of synonyms I'm using because I'm above that crucial midbrain diencephalic junction. So let's talk about sections of the brain. So when we slice the brain up, we create sections in anatomical planes, and they can be in one of 3 orthogonal planes, orthogonal named anatomical planes. We'll define these now. Or they can be an oblique section. An oblique just means it's not parallel to any of the 3 orthogonal planes. This is a nice example. This image from a human brain mapping paper shows a physical section, like a physical slice of the brain, right? This is just a prepared pathological sample of the brain, a corresponding digital section. And so this is an MRI that corresponds to this physical section, and a schematic. So these are 3 sort of common ways we see the brain. We commonly see schematics. We want to be able to move fluidly between schematics and particularly digital sections. You don't really want to get to the point of physical section, right? If you get to the point of physical section, you're dead. And so while physical sections are beautiful for learning, digital sections are really important diagnostically. So the first orthogonal plane, first of 3, is the coronal plane. So a coronal section is parallel to your face, like you've sliced your face off. And the name coronal actually comes from the section of the plane which approximately corresponds to the plane of section of a tiara-like crown. So crown, coronal. A synonym for coronal that's often used in other types of anatomy is a frontal section. But when we talk about the brain, we often use the term coronal instead of frontal, although both would be strictly correct. Horizontal plane, horizontal sections are parallel to the floor. You can see this is a section that's a horizontal plane. The ship is sailing on it. Here's the plane, and it's parallel to the horizon, horizontal plane. Equivalent terms for sections in humans are an axial plane or a transverse section. So those sections perpendicular to the long axis of the body. Those would be equivalent terms. And finally, we have the sagittal plane. So sagittal sections are parallel to the direction of an arrow shot. So Sagittarius is the archer, right? And if you take the plane, you can visualize it by imagining the plane that the bow and arrow lies in when the archer is shooting. So sagittal, Sagittarius. Divides the brain into left and right halves. Now, while there's many great resources for studying the brain in section, this is a really fantastic one, and it's developed by Dr. Claudia Krebs and her colleagues at UBC. I'd really encourage anyone to go in and play with this. So they've made it freely available, and you can label different sections in different planes of the brain. You can use functional labels to show you where things are. So if you want to label the basilar pons, the section will highlight here. It's a really, really great tool to explore. So again, challenge you with a few questions. I'd like you to describe this section using first an orthogonal plane and second an approximate rostral caudal level. Where are we in the brain rostral caudally, and how do you know? And you could use this tool to determine kind of where you are. The key is up here. So by rostral caudal level or position, I'm talking about how far back we are from the nose in the brain. Where in this section is the transition point between those fixed axes and variable axes? And finally, a little orientation question for you. Assuming this is presented in anatomical orientation or radiological orientation, yes. Where is the left thalamus? So if you can answer the questions in this video, then you've achieved the learning objective, which is confidently using neuroanatomical language to describe the nervous system, the language for orientation, relative position, and anatomical plane. Good job.